Find the damping ratio. In this problem, a complex single degree of freedom system is composed of two springs with the same spring constant, one damper with a known damping coefficient, a force, P, and two rigid beams, one massless and the other with a known mass. The damping ratio equals C tilde divided by 2 times the square root of K tilde times M tilde, where the tilde terms are generalized mass, damping, and stiffness variables, which depend on the system. The generalized equation for motion as a function of the displacement, z, is mz double dot plus cz dot plus kz equals p of t. If we assume the displacement, u, can be represented by the convolution of the shape function, psi, which is only dependent upon space, times a generalized coordinate, z, which is only dependent upon time. Applying this approximation to the equation of motion, the generalized mass, damping, and stiffness and force replace the actual values for m, c, k, and p, respectively. To solve this problem, we'll define the displacement, z, as the vertical distance at the far end of beam B, and we'll define z prime as the vertical displacement at the far end of beam A. Next, a 1-unit displacement is induced at the end of beam B, and we'll assume z minus z prime is non-negative. This unit displacement creates forces in the springs and damper. If we sketch out the free body diagram, we can show all internal forces acting on the system, which includes the force from the mass of the beam, the force from the damper, and the forces from the springs. We can develop an equation of motion by solving for the variables m tilde, c tilde, k tilde, and p tilde. And we'll begin by summing the moments about point A and setting the value equal to 0. Solving for z prime, the displacement at the end of this beam equals 4kz minus 2p, all divided by 5k. Next, we'll sum the moments about point B. Set that value equal to 0, plug in our value for z prime, and format the equation to match the equation of motion. After solving, the coefficients equate to 1/3 m for m tilde, 1/4 c for c tilde, 1/5 k for k tilde, and -2/5 p for p tilde. The problem asks to solve for the damping ratio. Now we can develop an equation for the damping ratio by plugging in the generalized values of mass, stiffness, and damping coefficient. And the damping ratio equals a function of the actual mass, stiffness, and damping coefficient. Plugging in the actual values for m, c, and k provided in the problem statement, the damping ratio equals 0.150. When reviewing the possible solutions, the answer is A.